Hi, my name is Ahmed. My name is Dawood.
And my name is Amro Amanuddein.
Yo, watch out! Oh. And hi, my name is Walter Ostrander. We are the Community Science Traffic Counter Group here at the University of Alberta. This is our capstone presentation. Our client is Sandra here at the Tomorrow Foundation, and we had a lot of help on this project from our technical advisors, Dr. Stephen Knudsen and Dr. Ron Anra. The goal of our project is to count traffic at community science traffic locations and to add context to existing air quality data. We met all of our functional requirements for the project. We even reduced the cost of the entire system by 55%. So as a whole, the project was a success. So let's dive into the presentation.
As you can see, currently I have my ESP32 camera set up. Now it's currently set up indoors, but the client, if they would like, can also set it up outdoors, especially since the ESP32 camera module is rated for temperatures of -40 degrees Celsius to 65 degrees Celsius. And I currently have it on a stable mount, just so that the frames could be stable when they are being transmitted over to the Pi. Now in the next segment, we'll be showing some example frames of what the ESP32 camera footage looks like. As you can see, this is an example of the footage that we obtained from the ESP32 camera module.
In this segment, we will cover the resources that we have hosted on Microsoft Azure in order to achieve the cloud functionality. So in here, you can see, we see four things. We see our subscription, the resource group, and the resource group houses these two resources that we have created. So let's dive into the first one, which is our PostgreSQL database. So in here, we can see that this is the PostgreSQL server that we're utilizing, the admin login name that we have, and the server name that we can use to ping it, as well as the configuration of the database. In here we can see we have 1 vCore, 2 GB of RAM, and 32 GB of storage. We can also see the amount of databases that we have in this flexible server, in which we're only utilizing the PostgreSQL. Now, the reason why we went with PostgreSQL instead of any other database on Microsoft Azure is because PostgreSQL allows you to have an extension known as TimescaleDB, which will make your queries more efficient as your timescale series data grows that is stored on the database, which we'll take a look at right now. So in here, if we open pgadmin, that allows us to open the database, we can see that we have two tables shown on the left right here. We have the traffic data, and we also have the device status. So if you take a look at the device status table, this is a table that stores the status of each device hosted at every location. In here we have the device ID, the status, and the longitude and latitude, and the last time the device pinged the database. If we now take a look at the other table that we have, which is traffic data, this is where all the data that is related to all the stations is stored. In here we have the ID of the actual row, the vehicle type that it detected, and the device that was actually responsible for pinging this vehicle, and the timestamp at which it detected this vehicle. Now all of this is stored on Microsoft Azure, but we need a way to visualize it, which is why we utilize the Grafana terminal hosted on our web application on Azure, in which we can access through the default domain. So in here, we have access to our Grafana terminal, in which we can go to our dashboards and view the visualizations that we have created. And in here, we can see we have three panels. We have the geomap that shows the status of every device with its location as stored on the database being reflected here. And since the devices have not pinged the database within the last 5 minutes, currently they all show as offline, in which case we will show them being online in another segment. On the right, we have another panel that demonstrates the device vehicle count. This is the amount of vehicles that were detected by the first device that we have, which is the only device we have set up right now and running and detecting. So in here we can see that we organize it in 5-minute buckets in order to demonstrate how many vehicles are being detected. At the bottom, we are responsible for demonstrating the total vehicle observations through a bar chart, in which we can see here. Now, we can also see a large influx of cars, which makes sense since the station is technically set up at a residential area, which means it encounters a lot of cars more than it does with bikes, buses, or trucks.
So I'll just be briefly going over the microcomputer, which is the brains of our project. We chose a Raspberry Pi for its relatively low cost and high compute power compared to other boards in its price range. The Raspberry Pi, or Pi for short, performs three main tasks for a project. The first is automatic connection to the ESP32 camera module, which after it's connected via Wi-Fi, it then receives frames and analyzes them to count traffic by vehicle type that goes by. The third task is to then update the database with accurate counts of traffic on that street.
All right, so you guys have seen this video before. However, there are some new additions here shortly. Yes, there we go. So these bounding boxes have appeared with numbers on top, indicating that we're actually successfully counting this traffic. And as you'll see, these statistics are actually being updated in real time on the Grafana terminal.
So as we explained previously, the Grafana terminal has three panels where we have the device status, the total vehicle count identified by the device, and the total vehicle observation that we have. So in here we can see that the device is currently online at the location that it's actually observing in, and it's currently detecting cars, which should draw the line chart here in a minute. And then we would also have the total vehicle observation, where we can see that we have just identified a bus that has just crossed by and the car. And in here, if we zoom out to the data range, we can see that over the span of 5-second buckets, it has identified 1 car, 4 cars, and 3, and so on. So now we pass it back to Ahmed in order to explain how the model works more in depth.
Right, so how do we actually accomplish this in real time on a Raspberry Pi? Well, there's actually two things going on here simultaneously. There's an object detection algorithm being run, and then second, there's an object tracking algorithm being run. Now, the object detection algorithm we chose to go with is based on the MobileNet architecture, and MobileNet was developed by Google specifically for edge devices, which makes it extremely efficient. We also then translated the model from TensorFlow into TensorFlow Lite, and then applied post-training quantization, which speeds up the inference time by roughly 75% with minimal hits to performance. So then the model, of course, outputs these bounding boxes, as I displayed earlier, as well as a percentage confidence in its prediction for what class that object corresponds to. We take those bounding boxes and insert it into our tracking algorithm. And this tracking algorithm is important is because we want to ensure we don't count the same vehicle twice. That's extremely important for our project here. So we ended up choosing the algorithm called ByteTrack. Now ByteTrack, where it differs from simple things like deep sorts and all that, is it deals very well with temporarily occluded vehicles. So you'll see here in the video, every so often a vehicle will be hidden by another vehicle that appears. However, when it reappears, other tracking algorithms will count that twice. ByteTrack actually keeps track of lost tracks for about 30 frames, continuously trying to predict where would that be if it's hidden behind something, and then reassociates it when it finally becomes visible again. So put that all together and you get surprisingly real-time counting on a Raspberry Pi.
Alright, so now that we covered each of the components individually, I'm just going to go over how it all fits together. As you can see, we have a component diagram here. The setup is quite simple. Once you receive the station in the mail or by any other means, you then set up the ESP camera module outside or anywhere with a view of the street. Following this, the Raspberry Pi will be connected via Ethernet, so you're just going to plug it into your modem or any other way, and you connect the ESP32 camera module to Wi-Fi with our easy-to-use script, which I'll show in a minute. Then the setup is complete, and it will automatically connect to the cloud environment, and you'll start seeing data visualizations basically immediately. So next, I will just cover improvements that we made from the original prototype that we were given. So we reduced the prototype cost by 55% from that original prototype. Another improvement we made is that we created cloud architecture, including a database and website for data visualization. Furthermore, we send status updates from the Raspberry Pi to the database so that community members can see a map, like this one, of all the stations and their online and offline status. Another ease of setup improvement that we made was eliminating the need for drawing counting lines. So the original prototype that we were given required, upon setup, for this line to be drawn across the road so that when cars passed it by, it could count as they crossed that line. We eliminated the need for that. We also created a Wi-Fi reconnection protocol so that if the Wi-Fi changes or during setup, it's easy to get the station back up and running. So I'm just going to show that process now. Once you connect the ESP32 into Wi-Fi, you should then see this Auto Connect AP network. Connect to it, and then once you open a new tab, if it works properly, you connect, and it should open a network login page, which takes a minute to load. You then click Configure Wi-Fi, and then click your home network. So after you enter the credentials, it will reboot and connect itself to Wi-Fi, and the Raspberry Pi will automatically find it on the home network, and the setup will be complete.
So here I'll elaborate on how we ended up concluding on this approach. There were three main approaches considered for this project. The ML on board approach, where at each of the traffic stations, we have a board that is processing the obtained frames. The ML on cloud approach, where the ML models are running on the cloud. ML on the hub approach, where there is a physical centralized processing station or server where the ML models are running. And here ML just stands for machine learning. So out of all the three approaches, how did we decide on choosing the ML on board approach? We ran an experiment where we set up the camera in a high volume traffic location and found the number of frames where motion was detected per day in a week. We then found the weighted average of the number of frames collected in a week, and based on that, we calculated the cost for a different number of years of operation for two different numbers of stations. So in this case, as you can see from the graph, we calculated for 20 devices, and we have an upper limit of 50 devices. So from the graph, we can see that the on-hub approach is cheaper when scaling up to 50 stations. Now, this is because there's a lower variable cost as compared to the other approaches, but the entry cost for setting this up is much higher when comparing it to the other 20 solutions for 20 stations. The other issue for this approach is the fact that there is one point of failure, which is that centralized hub, and it cannot handle and if it can't handle the estimated maximum processing load in real time, then there will be issues later on. So as a result, there's no guarantee that our 5-minute refresh time will be satisfied. The on-the-cloud approach is relatively cheap for the first year of operation. However, over the years, you can see the cost ramp up, and this is mainly due to the different number of services that are required to get the system operational. Now, finally, the ML on each board approach, which is the approach we are currently going with, is the cheapest option when setting up 20 stations and has the lowest entry cost as compared to the other options. Also, when it comes to setting up more stations, it is, yes, more expensive than the ML on one hub approach, but since each board is dedicated to running a single model per station, the performance would be better.
Alright, so what worked and what didn't work? Well, honestly, all parts of our product worked really well. We managed to hit all of our key functional requirements. The only issues that we really faced and what really didn't work as well as we hoped was the actual counting algorithm itself. As mentioned before, the counting algorithm is comprised of both a detection algorithm and a tracking algorithm. The detection model is kind of where we face the most issues. As you can see from this video, some of these cars are being classified really well, however, others aren't really being counted. And it's mostly to do with the dark cars. We tried a lot of different architectures, and the main challenge here is trying to find a good enough model that will still run in real time on the Raspberry Pi. So after attempting to fine-tune our own, none of the results were really satisfactory, and we were only able to get up to around 60 to 70% counting accuracy when we were initially aiming for that 90%.
As stated previously, the expected outcome of the project was to create an easy-to-use, low-cost traffic counter system for community members to deploy in their homes. This will add context to existing air quality data. Within 3 months, we created a user-friendly counting station that is 55% cheaper than the previous prototype. We also created new functionality such as an easy-to-use Wi-Fi reconnection, an infrastructure to store and display traffic statistics in the form of a website at no additional cost. Furthermore, this website is able to display counting station status, indicating if they are currently online or offline. Some future improvements include unifying the two boards into a specialized board for machine learning models, further reducing the cost, and increasing compute power and decreasing setup complexity. Over-the-air updates is another possible improvement to enable model updates remotely, and finally, increasing the counting accuracy by getting a better detection model. Overall, we had fun, accomplished our goals, and learned lots during this project. Big thank you to our sponsor Sandra at the Tomorrow Foundation, along with Dr. Stephen Knudsen and Dr. Ron Unrau for all the help and advice guiding us when the going got tough. And finally, thank you at home for watching.